Hello everyone. In chapter 1, that's where we are. Chapter 1, we're going to take on the topic of probability. So in section 4.1, we're going to begin by talking about some of the basics of probability. We're going to have primarily some definitions and the terminologies again that go with probability. So there's not so much in the way of formulas in this section. We'll have those later on. So let's begin with the idea of what is probability. Before we do, though, I need to clarify some of these jargons. Okay, again, these are some terms that we would like to be able to define them. Now, as I go down the list, each new terminology sort of relies on the prior one. So let's begin with data. So what is data? Well, data is going to be any information that you collect on the variable of your choice, the research variable. So for instance, here I have example of a person's weight. So if I, let's say, record my weight, your weight, anybody's weight, then that forms or becomes a data point. Next, we have an experiment. What is an experiment? An experiment is any activity that generates data. Okay, so it could be as simple as tossing a coin, or it could be as elaborate as trying to, let's say, divide people into groups and administer maybe drugs to them, or any sort of activity that's going to produce data for us. I may be able, or I may be interested in finding, let's say, the stopping distance of automobiles. So the experiment here is to actually observe the stopping distance of each automobile as they slam on the brake. Then we talked about trials. A trial is a repetition of an experiment. So if I have, let's say, the case where I'm tossing a coin. So if I flip the coin twice, that's two repetition of that experiment. The experiment is the toss of a coin. So I have two trials of that. If I flip the coin twice, I have two trials of that experiment. Then we talk about outcomes. So what is an outcome? An outcome is a specific result of an experiment. It's what happens when you conduct the experiment. That's going to be the outcome. Okay? So let's say you toss a coin. If you observe a head, that would be the outcome. Again, the outcome is what could happen when you conduct that experiment. Then we talk about the universe or the sample space. The sample space is going to be the collection of all possible outcomes of an experiment. Okay, so for example, again, if I pick a random page from the page of your book, suppose the book has 500 pages. And I'm just looking at a page at random. So one outcome would be to observe page number 50. The sample space would be all pages from 1 all the way to page 500. So that's what the sample space is. All that could happen when you conduct the experiment. And then we talk about events. Okay, so events are going to be collection of outcomes. They could be a single outcome, okay, or they could have more than an outcome. If it happens to have a single outcome, just one outcome, then that would be a simple event. If event could possibly have two or more outcomes, then it's called a compound event. So for example, when I look at a page, suppose I define event to be to observe an odd number on the page of a book. Well, I could observe any single page, right, that is odd. So if I define, for example, event E to be to observe page number 57, that would be a simple event because there's only one page, page 57. Now, if I wanted to say, well, what if I want to observe an odd number page? Well, there's a whole bunch of odd numbers between 1 and 500, right? To be exact, there's 250 odd numbers between them. Half of them are odd, half even. So that's going to be a compound event. Okay. And so let's define probability now. So those are the terminologies that we want to be familiar with, so we know enough in order to go forward. So with probability, the probability is, we're going to call it the likelihood of occurrence or non-occurrence of an event. Okay, that's all the probability is. What are the chances that something will or will not happen? Now, some people talk or think as probabilities in terms of odds, like what are the odds of something happening? It turns out that actually odds are not probabilities. Okay, there is a close tie between them, but they're not the same thing. So if I say, what are the odds that it will rain tomorrow? I'm not going to say the odds are 50%. Okay, that became a probability. The odds, just so you know, the odds are actually the ratio of two probabilities. Probability that something will happen divided by probability something that will not happen. So those are the odds. And odds are usually stated as ratios, like the odds are 3 to 1, 5 to 7, 10 to nothing, whatever. But with probabilities, we're talking about the likelihood that something could happen. You're familiar with probabilities. You probably make the statements yourself. You hear about it all the time. Like, what's the probability of rain this weekend? What is the probability that an automobile, let's say, will have a flat tire on the way to work? Those are probabilities. Now, when we talk about the likelihood of an event occurring or non-occurring, I just want to clarify, when do we know, or when do we say an event has occurred exactly? What do we mean by that? So, we say that an event has occurred if any one of its outcomes are observed. Okay? Any one of its outcomes actually happen. So, we're going to look at the examples later on, but suppose I roll a die and I'm going to define event E to be to roll a 2 or a 4. Now, if I roll the die and I observe a 2, I'm going to say that event just happened, just occurred. Even though I didn't see a 4, but I saw a 2, but my event was a 2 or a 4. So as long as one of the components, one of the outcomes occur, the whole event has occurred. Now, having defined probability as a likelihood of something happening or not happening, how are we going to measure probability? So, it turns out that there are 3 approaches to probabilities, or to assess probabilities. Okay? So we're going to go through these 3 approaches. The first approach, the first of these 3, is called the subjective approach. With subjective approach, it's really just that. It is not an objective method. It is subject to the person or individual that actually makes the statement. So if I say, what is the probability that, for example, we're going to have a vaccine by next week? I don't know. What is probability that I'll be late to work tomorrow morning? I don't know. Asking me, let's say probability I'll be late going to work tomorrow. Well, let's say I've never been late going to work. So I'm going to say the probability of that is 1 in 1,000. Where did I get 1,000 from? I just made it up. But technically what 1 in 1,000 mean is this. If I look at, let's say, the last 1,000 days, work days, I've only been late 1 time. And that made it 1 in 1,000. So, with subjective probabilities, again, it's subject to the person that makes it. So, let's say for America Got Talent, you ask the panel of the judges that are sitting in the front. Let's say there's 3, 4, however many there might be. And you may ask who's going to be the next winner of the America Got Talent. Each of them will state their own opinion, right? And that would be the subjective idea of probability. The probability of a flat tire on the way to work, I'll give it 1 in 10,000. That's just my experience. Now, we're not going to deal with subjective probability you can kind of see if we did how that could turn out. Each person will have their own probabilities, and we could all be correct. We could all be right because it's subjective. Because with probabilities, there is no right or wrong. And I'll emphasize and tell you more about that in just a few minutes. What I just said, there is no right or wrong. Let's look at the second approach. And so just to kind of put this one to rest, we are not going to do subjective approach to probability for obvious reason, because we want to be objective. We all want to get the same numbers, same probability statements. So that brings us to our next approach to assessing probability. That's the classical approach. Now I have 4 things here going for the classical approach, right? These are the 4 items that must be in place in order to find probabilities using this approach. One of the assumptions of classical approach, the very first one, is that the outcomes that we observe are equally likely outcomes. Now, when we say equally likely, it means each of those have equal chance of occurring or happening. The second presumption for classical approach is that if the experiment is repeated, the trials must be independent. Now, we're talking about independence in a statistical sense. So when we talk about independent outcomes, we're talking about outcomes where occurrence or non-occurrence of one has no bearing on occurrence or non-occurrence of the other. So that would be the second presumption, independence of outcomes. And the trials must be identical. That means however you do the experiment, it has to be done exactly the same way. And finally, the probabilities that are found through classical approach, they are exact probabilities, and these models are exact models. So what we mean by exact is that because with classical approach, the probabilities are modeled mathematically. Usually you don't conduct the experiment actually. Okay, so for example, if I want to know what is probability of a tail in a flip of a fair coin, I don't need to get a coin out and actually flip the coin. I can say, well, there are 2 possible outcomes, and there's only 1 tail, 1 head, so the probability is going to be 1/2. So in that sense, the probabilities are exact because I have a count for the numerator and a count for the denominator. And this is how you actually see it now written as kind of a formula. All it is a ratio of 2 numbers. Now in this statement, probability of event E is NE over NS. NE is the number of outcomes that are favorable to event E, and NS is the total number of possible outcomes in the universe or the sample space. Okay, and keep in mind all probabilities must lie between 0 and 1. So I cannot overemphasize a probability by calling it 110%, and I cannot understate a probability by going negative, like negative 20%. It's not going to happen. So the correct numbers are 0 to 1, meaning 0 to 100%. Okay. Now, as far as reporting the numbers for probabilities, we usually go with decimals. Okay, but it doesn't mean we couldn't go fractions or percents. The interpretation, however, usually is in percent, right? Like there's 50% chance that something will happen. There's 80% chance that you will be stopped or you will be cited for using your cell phone on a freeway. Whatever those probabilities are. And there is another subjective probability. What is the probability that you'll be cited for using for texting and driving on the way home? I don't know. I'll give it 20%. That's subjective. Somebody else says, no, 15%. Someone else may say, oh no, that's 80% because of where I live. There is littered with cops, motorcycle cops, and they give you a ticket. Okay, so however you do it. Now, if we do it as a decimal, just keep in mind, usually we round it to the nearest 10 thousandths. That means 4 digits beyond decimal point. Okay. Now, when you do this, let's say in my MATLAB, you just have to watch for the instruction. It tells you how to round them. Usually, they say to 4 decimals. Okay. Now, something that's important with, again, a classical definition of probability, that you don't have to conduct the experiment, and the problem is modeled mathematically. And so in order to be able to actually model this problems, let me go down, model these problems, we should be able to count the numerator, count the denominator, that is the number of outcomes. And usually the counting techniques are some kind of a permutation or combination for us, the way we count these items. It's not your straight counting, as simple as head or tail kind of thing, type counting. Okay. Now, what are impossible and sure events? If something could not happen, possibly couldn't happen, that's going to be an impossible event. So what is the probability that the sun will not rise in the morning? Impossible. That would be 0. And by contrast, if something has 100% probability of happening, then it's called or known as a sure event. So a sure event is sure to happen. So what is the probability that, for example, we will have snow in the next 5 minutes, and suppose we're in the middle of a summer heat wave? That's going to be impossible. So that's going to be 0. And what is the probability that it will not rain? Let's say when the skies are clear, probability it will not rain, that's a sure event, 100%. What is the probability that a number between 2 and 10 have at least one odd number? What is probability of at least one odd number between 2 and 10? That's a sure event, because there are 3, 5, 7, 9, and I said at least one odd number. So, okay, so we talked about it. Now, as far as I mentioned earlier, with probabilities, there is no right or wrong answer. Okay, now there is the right answer, how we find what we're going to state. I'm not saying just make up your own numbers, and because I said there is no right or wrong. What I mean is this. Let's say they tell me probability of showers. I have it here. 80% chance of showers this evening. Now, suppose the evening comes and goes, and there's no showers. So does that mean it was right or wrong what they told me? That's the kind of right or wrong I'm talking about. With probabilities, they just give you your expectation of an event. It doesn't mean an event will or will not happen, unless it is an impossible or a sure event. So even if something has a 90 plus % chance of happening, there is a chance that it may not happen. Think about, let's say, winning the lotto, California lottery. Probability of winning the lotto is about 1 in 172 million. Okay? So, the probability is very dismal. That doesn't mean nobody's going to win. Sometimes people win the lottery, right? So, it just gives you the expectation, and you can sort of be prepared for it. And in other instances, people can manage uncertainty under these conditions. So that's what I have here. Probabilities are used to quantify and manage risks and uncertainties. So there is no right or wrong when it comes to probability. That's what I was trying to clarify. So let's take a look at an example here. So in this example, I'll show you one piece at a time so it's not confusing. So here I made up an example. Let's say our experiment is the roll of a fair die, 6-sided die. And I have defined 3 events, E1, 2, and 3. Okay. And E1 is to observe a digit less than 5. That means 1, 2, 3, and 4. Event 2 is to observe a prime number. Now prime numbers in that list are only 2, 3, and 5. 1 is not a prime. 1 is a unit. So it's neither prime nor composite. And remember, prime numbers are divisible by themselves and 1 only, or you can write it as product of itself and 1. E3 is to observe an even digit. The even digits are 2, 4, 6, between 1 and 6. Now, we want to, once you define, and notice by the way how I defined events. Usually the experimenter, the researcher, defines events in context of the problem. And then we want to find the probabilities of those events. So I defined event E1 to be whatever it is, 2, 3, so on, to be what they are. Now, once we define them, we like to find the probability of those, right, of each of those events. Now, the sample space here, all that could happen, right, the universe of outcomes. For this experiment, any of the digits 1 through 6 could occur. And because it's a fair die, that means all of these outcomes are equally likely. So it meets the requirement of the classical definition of probability. And because of that, I can actually find these ratios now and find those probabilities. Note each event has its own probabilities. So probability of E1, 4 possible outcomes out of 6. 4 favorable outcomes out of 6 possible outcomes. 2/3, 0.6667 rounded to 4 decimal, or as a percentage is 66.67%. And the next 2 probabilities, each of those events have a probability 50-50 shot at it. Okay. And there you have it. Now notice, by the way, here, events E1 and E2 have common outcomes, right? In fact, E1, E2, E3, all of them share a common outcome. So let's say I actually pick up a die and I roll a die. And I observe a 5. I roll the die and here it is, I see a 5. So which of these events just occurred when I roll a 5? Well, event 1 couldn't have occurred, right? Because there's no 5 in the list. So E1 did not. 5 is one of the outcomes of event 2. So just because I observed the 5, it suffices to say event 2 has occurred. Event 3 didn't occur either, just like 1 didn't, because 5 is not in the set. If I roll a 2, event 1 has occurred, event 2 has occurred, event 3 has occurred. So all 3 events had occurred. So this suggests that these events could occur together, right? They could occur together or each on their own. Okay, now, again, I want to emphasize that with classical definition, you don't have to actually conduct the experiment. So, and the probabilities are exact. The reason, again, it's exact because you have a very definite count for the numerator, a definite count for the denominator, and these probabilities are exact. We're not talking about exact in the sense that you get an exact number. Okay, my probability, like in the probability of E1, this number 0.66666666, so on forever, right? That is not an exact number. Exact number is 2/3. So We're talking about the fact that you have ratio of two deterministic numbers, 2/3. That makes it exact. In other words, everybody that conducts this experiment, for everyone in the world, probability of this event E1 is 2/3. It's not like who conducts the experiment, because it's modeled mathematically. Let's look at the last approach for this section, and we'll be done with this section. The last approach to assessing probability is the empirical approach. Now, the word empirical means based on actual experiment. Okay? So with empirical probabilities, you have to, or empirical approach to probabilities, we have no choice, we have to conduct the experiment. Okay? Now, when we conduct the experiments, and these numbers, I don't know why they're like this. Oops, sorry. Hold on, let me fix the numbering here. Hold on. Okay, I went ahead and put those Roman numerals 1, 2, 3, 4 here. So these are the assumptions that go with the empirical approach. 1. Again, like classical approach, we take the outcomes to be equally likely, and we assume that the repeated trials are independent. Remember, repetition of an experiment is what the trial is. The trials must be identical, means they all must be done the same thing. So let's say I'm using a digital scale to weigh a package. In the middle of the experiment, I cannot switch and change it to a different digital scale. I have to use the same instrument, so the trials are done in an identical manner. Okay? Now, the next item is, let's see, the probabilities themselves are not exact. Okay? So that's very important to note. The probabilities that we get from empirical approach will all be approximations to the real probability. Okay, to the real probability. Now, the reason for that is because we conduct the experiment, and each person may conduct it in a slightly different manner, and the number of trials may vary. Because as you will see in the formula, the probability depends on the number of trials that's conducted. Okay. Now, here's how actually the empirical probabilities are found. You take the ratio of how many times event E has occurred in the experiment that was conducted over N, which is the number of trials. That N should look familiar. It's the sample size, isn't it, that we use in chapter 3. So that's how we find those probabilities. Okay. And let's see. So the probability is the ratio of frequency with which event E has occurred over the total number of trials. Now we have the symbol tilde. That means approximately equal to. Okay, so the ratio of two numbers approach the probability. The ratio of F to N approaches the true probability. So that's what is going on with this one. And these, the fact that it approaches the ratio in the formula. Let me see, I have a more specific. This means the ratio of left to the right side approaches 1. Okay. I'm talking about the ratio of left side, and left side here, probability of E, to the right side. That ratio approaches 1 as N gets large. So what empirical probability, what makes it work is actually a law that is called the law of large numbers. The law of large numbers, which says as you increase the number of trials, the probability, the observed probability, or I should say the experimental probability of E approaches the actual probability of E. The expression to the right of tilde here F over N. This is what the experimental probability is. Okay, to the left is the actual probability of event. So the actual probability of event E is proportional to the experimental probability of E. What does that mean? It means what's down here now. That means the ratio of the two approaches 1, they become the same. Now in your book, the author actually has a picture of what's going on here as far as the law of large number goes. Maybe I'll do a cut and paste for you later on at the end, and I'll show you what that law of large number tells us. Okay, so, and there I have it here. The theoretical justification for this is a law of large numbers. And now, who's to tell how large n should be, by the way? That's why the sample size for us a lot of times determines what n is. So if you take a sample of size 30, then you've chosen your n to be 30. If your sample size is 1,000, then that's what n is chosen to be. So let me now show you this law of large numbers. Okay, so what I have here is actually a clip from the page of your book to illustrate the usage of the law of large numbers. So what the author has done here actually is he's looking at simulation of tosses of a fair coin. Now we know the probability of head or tail is 50-50. So that is what this probability is, 50%. Now what he's actually doing is he's down below here on the x-axis. He's looking at the number of tosses. He tossed the coin, let's say 1 time, twice, 3 times, so on. 10 times, 20 times, 30 times. He does it 100 times. So notice when the number of trials are small, these probabilities fluctuate at first. So let's say on the first flip of a coin, you have a zero hits. So the probability based on 1 flip is 0%. Impossible to observe a head. Suppose you flip it the second time, still no head. You still say probability is 0, but we're not going to believe that because we just haven't done this long enough or large enough number of times. So what I'm going to do is I'm actually going to, let's say, throw it one more time, flip the coin one more time, and suppose we actually see a head now. So the probability is 33% now. So notice how probabilities fluctuate. They're not exact in that sense. They change depending on the denominator. And the denominator has to do with how many times we conducted the trial. But in both simulations here, as number of trials increases, again, initially notice things look different. But ultimately, in the end, near the end, things stabilize toward the true probability. So that's what the law of large numbers says about empirical or experimental probabilities. Do these large enough number of times, and the true probability will emerge out of empirical probability. And that is why we like large samples. So imagine your sample size here is 100, and you're pretty close to the actual probability of that event. I'm going to also show you this in StatCrunch. So I'm going to go and look at the simulation in StatCrunch. Let me get there. I like to get there from dataset from your book. And we're now in the StatCrunch. I'm going to go applet, and let's do simulation of dice. Okay, so I have a 6-sided die, and the number of dice to roll 1. You can roll 2, 3 dice at the same time, but I'm going to roll 1 die. Okay, so let's roll the die 1 time. Again, with 1 run, see, there you go, we observe the 6. Okay, let's roll it again, and there you go, that's where that is. Let's roll again. Any one of the numbers 1 through 6 would be equally likely, right? Run it this time, we observe a 3. Now if I run it 5 times, I would expect maybe 5 different numbers, maybe. It doesn't mean we couldn't repeat a couple of 2s or a couple of 5s or a couple of 6s. So there you go. Notice that was a 4, 3, 2. So we had actually more 3s so far happening. Now let's do it 5 more times. We haven't observed, interesting, we haven't observed that we've tossed or we've rolled this die total of 7 times and no 5, no 1. See, that's what happens for small samples. Things may not happen the way you expect them to happen. And still, no 1, no 5 out of 12 runs a roll of a die. So if I want to know what is probability that I roll a 5, according to the 12 trials, the probability is 0 because I don't see a 5. Same with probability of 1. Let's roll 1,000 times now. A different picture now, huh? Now, if things were equally likely, which is the case with roll of a fair die, 6-sided die, you would expect these bars to be exactly the same height. That means they're equally likely. Now, if I hold the mouse over this, looks like I have 167 out of 1,000. Remember, probability for any one of those numbers is 1 out of 6, right? Now 1 out of 6 is about 17%. Look at this one. 167 out of 1,000 is almost 17%. Look at that one. 169%. The exact number is should be 167 almost to be equally likely. That one is 186, a little bit over. 163, a little under. 171. See, they're on or about 170. This is the lowest one, 156. So again, I just want to show you what we mean by equally likely outcomes, and this is the reason. So these numbers, based on this, I can say probability of a 6 is 156 out of 1012, and that would be the empirical probability. Okay, so with that, we are done with this section. Again, the key idea was definition of probabilities and the 3 approaches to probabilities. With that, we are done with this section.